Alright, so let's get back to proving the X-independent theorem. So just to recall, last time we defined the set. Well, just to recall the whole setup here briefly, we had this map pi from the additive group, the multiplicative group, which exponentiates each variable. We had a v in c star to the n and a w in c to the n, such that w is pi inverse v. Right, we define this I, definable set. We all transit to w, such that if you look inside the fundamental domain, it was contained inside pi inverse v in the fundamental domain, and it wasn't empty. And we showed at a number of integer points of I, so certain rational points of height, of height of most t, grows linearly in t. Okay? And so as a result, by the Pila-Wilke theorem, we conclude that I contains semi-algebraic curves, which we showed can be upgraded to complex algebraic curves. So I contains a semi-algebraic curve C, which we showed, so a semi-algebraic holomorphic curve C. So we can't upgrade C to a full algebraic curve because of this condition, which might cut off a compact piece of C. But at the very least, it contains sort of an algebraic curve C, and you have some sort of piece of it cut off by inequalities. I contains that piece. Okay, so Pila-Wilke actually says more. We're going to need the version which gives us finitely definable families. But first, I just want to explain how we use this algebraic curve C. So now what we're going to do is, if you remember, we assumed at the very beginning that you have this sort of setup without there being a special guy between W and pi inverse V to get a contradiction. So now we're going to set up the induction nicely. So assume by induction that sort of the triple n, the dimension of V, and the dimension of V minus the dimension of W is minimal lexicographically. Okay, so for our counterexample, we're going to take smallest n, and for that smallest n, we take counterexample with smallest dimension V, and for that, the counterexample with smallest s. It's just an induction argument. This is the easy way to set it up. Okay, so now assume the way this works is we have a family of transits of W parameterized by C. So first, assume that this family of transits of W is not constant, so it depends on little c. Right? All of these translets satisfy that they inside up to the n, they sort of have some piece, and they're inside the preimage of V. Okay? So in that case, you can define this W prime, which is a thickening of W. You glue together all of these translets. Because they're not constant in little c, the dimension of W prime is the dimension of W plus 1. This is taking a one-dimensional family and putting things together. And by analytic continuation, W prime is in pi inverse of V. Because in f to the n it is pi inverse of V, and there's something in f to the n, so it will holomorphically continue. This makes sense, everybody? So it's very, okay, so then this is so then, moreover, there can't be a special subvariety between W prime and V, because then it would certainly be between W and V. Right? Okay, so this gives a smaller counterexample. So contradicting the Arminian-Maliki assumption. Okay. So that's, it's sort of key for this that we have CB algebraic, right? If it was just an analytic set, this argument wouldn't be the same. Okay. Okay, so therefore, we can assume that this sort of family of varieties is constant for all connected algebraic C. So any curve C, this kind of thing has to be constant. Okay, so now we use the group structure. So we'll let H be, let me let theta be a stabilizer of W. What does this mean? All the guys in C to the n that W plus T is equal to W. So it's not hard to see that theta is a group. Okay. Yeah, that's the blue relation. Theta is a group. Okay, so the other thing is that these curves C we find contain rational points. In fact, many rational points, right? So, I think we can find C, so by Pilogluki, By the strong version, where we take not just every algebraic thing inside I, but we know that in fact the rational points in I are contained, of height t are contained at most sort of t to the epsilon guys in some fixed family, we can find an algebraic C in I with arbitrarily many rational points, like integral points. And so, sorry, I want integral. Well, it doesn't actually matter. Yeah. So the integral points of z is infinite. And so take h to be the connected component so the identity component of the group generated by the integer points. So let's write it down more precisely. Sorry. So what you can do is let h be the identity component of the smallest algebraic subgroup of theta containing all the integer points. See, the point is that theta is a group, but it might just have sort of one, it might be high dimensional, but it's have a line of integer points. And I sort of don't want all the stuff that's not generated by integer points. So we just want the rational part of theta. So if we let h be this, then the dimension of h is positive, and h is a Q linear subspace. And everything in h is generated by integer points. The slope of h is rational. So now we have a rationally sloped group, which fixes that. Okay. Now the idea is to use rationality in the following way. Now assume okay, so we know that W is fixed by H. Otherwise we could increase it and get a smaller common example. We're going to use a similar argument on V now. But it's a little tricky because there's no direct sort of action downstairs of C V. So what we do is the following. Assume pi inverse V is not H invariant. So then what we do is, well, since by our choice of H, the rational points are dense inside the real points. V can't be invariant by the real points. So we can take a rational point, which V is also not invariant by. It can't be invariant by all of this without being invariant by all of this, and therefore by all of H. You can pick little h in HQ such that little h times V times pi inverse V, I apologize, is not equal to pi inverse v. Okay, and so now define v prime to be pi of h plus pi inverse v. Sorry, this is plus, right? The action's additive. You're getting addition. H plus pi inverse v intersect pi inverse v. Now that I think about it, probably in the abelian case, it doesn't matter that h is in h of q, so h. Probably a complex h would have been enough because it's abelian. But it definitely wouldn't have been enough for it abelian. So this is important looking ahead. Okay, so then the point is so v prime is a variety. Okay. Actually, I guess in this case, so I guess in this case you don't need to assume little h is a rational point. You can take little h to be an arbitrary point in capital H. Because in this case there is an action downstairs of the torus, which commutes with the action upstairs of the line. Right, so I mean pi of h plus pi inverse v is just e of h, now an element of the multiplicative group, multiplied by v. So that's clearly a variety. If v is a variety, it's multiplying the coordinates. And so this is a variety, v is a variety, you intersect them, you get some smaller variety. Okay, but now by assumption, pi inverse v prime is h plus pi inverse v intersect pi inverse v, and both of these guys contain w. Right? And dimension v prime is less than dimension v because we assume these two guys weren't the same. So now again, this contradicts minimality. So instead of equating w, now we're shorting v. So therefore, we get that v is pi inverse v is invariant by h. Okay, so now the idea is to apply induction. So it's not totally hard to do it, but it's not too hard. So then changing coordinates. So Q linearly, we can assume that V, well, pi inverse V, well, yeah, we can assume that V is C star cross some V naught, or V naught is in C star to the n minus 1. Like we can assume that H contains some cube linear group, we can assume it contains the base of the vector 1 and the rest being zeros, and that just means we can change the first coordinate arbitrarily. So we've now reduced to the case where V is just a fiber of a single variety in n minus 1. So if W were also would be done, but so we can finish sort of by doing the following. So W is in C cross sort of, let me call this pi n minus 1 now to record the dimension. Pi n minus 1 of V0. Okay, the only thing to deal with is the fact that W could actually be changing fiber by fiber. Right? Okay, but now what we can do is we can take W prime just to be the projection of all of W onto this coordinate. Just sort of union up all the fibers. W prime be the sort of projection onto Cn minus 1 of W, which is inside V0. And so now the pair, the triple n minus 1 W prime V0 provides a smaller lexicographic counterexample. A smaller counterexample. All right, and so that contradiction finishes the proof of the theorem. Okay, so it's a little windy. Let me just summarize it on the blackboard, because there's a lot of stuff going on. Even though the idea is quite simple, but somehow I want to define this I. But handling all the cases is a little unwieldy. Okay, so summary. So the first part, here's sort of what's really going on in this proof. The first part is we use Peter-Wilke to get a curve C such that W plus C V is a family of counterexamples. That's somehow the main step, finding this clever set, clever definable set, and applying Peter-Wilke, we automatically get a bunch of translates of W which are inside pi and V. Okay, so then if W plus C is not constant, we thicken W. If pi inverse V plus C is not constant, we shrink V. Finally, if this is constant, we just reduce to n minus 1. That's somehow a summary of what's going on in the proof. The rest is just like careful bookkeeping, so to speak. Any questions about this argument? There's sort of a variety of things you can do using this idea of finding slightly different eyes and finishing in slightly different ways. They all require some amount of being careful, and they're all sort of roughly based on the same idea. Okay, so let's get back now to our, I don't know, fifth proof of Length conjecture or something. So we defined this, we proved this X-Lindemann statement, which is an important point. It sort of tells us that if we have an algebraic guy upstairs, inside an algebraic guy downstairs, there's a special guy inside. And combined with this Galois theoretic argument that rational points have large Galois orbits, this gives us sort of a lot of special guys. A lot of torsion cossets. So there's one sort of thing which is left to deal with in this whole, in this proof. Sort of, everything is essentially straightforward now. The thing you have to be careful of is, and we talked about this in our earlier proof as well, is you have sort of infinitely many families of torsion cossets, depending on the slope. Right? And last time we talked about this, we dealt with it through an vector distribution argument, which is fine. So it turns out homonymity provides you sort of a nice way of handling this as well, without dealing with anything so heavy as equidistribution. So I want to sort of talk about sort of the finitely many slopes argument. And it works in the following way. So suppose we have V in C to the n. And we want to understand those T's in V, which are torsion cossets. And I'm going to insist that T in V is a maximal torsion cosset, not contained a strictly bigger one. And the following claim allows for sort of an easy reduction of Length's conjecture to the X-Lindemann theorem, and doesn't rely on anything we did before. So claim that T, so sort of the set, how should I say it? So maybe let me T is a maximal torsion coset, and let me write G sub T to be the sort of stabilizer of T. So in other words, G sub T is just the group, the subtorus that T is a translate of. Okay? So if T is a point, then G sub T is just the identity. So claim the set of G sub T is finite. So this claim allows us a priori to restrict yourself to looking at sort of a finite family of torsion cosets. Is the claim clear? Okay. This proof is a nice illustration of how homonymity can be used to get rid of sort of otherwise hard arguments.
Wait, I'm not sure.
Yes.
So, what is the claim exactly?
So if you look at the algebraic guy field, and you look at all maximal torsion cosets inside it, there might be infinitely many, right? Like, for example, it might all be points.
Oh, T is varying?
T is varying, yes.
Okay, I see.
Yeah, yes. That's T varies.
Okay.
That's right. Yeah. Okay, so the idea now is if we look at pi inverse t, so take L in pi inverse t to be a component of the inverse image of t, which intersects a fundamental domain. So this keeps L definable. Well, what we're going to do definable, sorry, L is already definable. So L is some translate of a Q-linear subspace. So in claim there is no linear subspace L prime which strictly contains L such that L prime is in pi inverse V. Okay? So if I replace linear with Q linear, then this would be obvious because of the maximal torsion coset part. If it was Q linear, you could push it forward and get a larger torsion coset inside V, which contains T. So this claim is subordinate to this thing. Sorry, that's confusing. Okay, so the proof is very easy. So otherwise, if there was such an L prime, then we could apply X Lindemann again and get an even larger Q linear subspace. Right? So if not, by X Lindemann, which we just proved, we know that the only intermediate guys between algebraic guys, in particular L prime qualifies, and algebraic guys downstairs, in particular V, are Q linear guys. And X Lindemann can find L double prime between these two guys such that L double prime is Q linear, but then if you project L double prime, you get a larger torsion coset in V. And that's a contradiction. So in particular, the maximal linear subspaces inside pi inverse V, we know have rational slope. They're all Q linear. Okay? Let's write that down. Maximal linear subspaces in V. So I don't know if you mean coset, right? I mean linear subspace coset. Linear subspace cosets. Have rational slopes, they're Q linear. Okay, on the other hand, oops. On the other hand, the set of such guys is definable. Right? If you let I be the set, I'll be a little informal about this. So linear subspace cosets L such that L intersect F to the N is in pi inverse V intersect F to the N, and L is maximal. This is definable. Right? Because this set is definable, that's T. Iterating over all such L is a definable thing to do. You have to stratify by dimension, but there's finitely many dimensions, so that's not hard. You can write down coefficients of the equation. And saying it's maximal is also easy. You're just sort of saying there's no guy with bigger dimension, which satisfies it also, which contains L. So this guy is definable. And now we can let J be the linear subspaces whose cosets are in I, with at least one coset in I, basically. So in other words, just the slopes of the guys appearing in I. And so now J is definable and discrete. So J is equal to the set of its rational points. Right? So a definable set which is discrete has to be finite. Either by cell decomposition or just immediately by homonomiality, just project down to each coordinate and you get something. To get a finite interval, it's got to be a finite set. So therefore J is finite, and that's exactly the commitment. Okay. Okay, and so now, sort of finishing the proof of length conjecture is easy. So let's sort of T, let's say T1, let me call it G1 maybe. So Gn be the finitely many tori whose cosets give maximal torsion cosets in V. Okay. And so now for each GI, we can let H1 through Hn be complementary tori. So in other words, so Gi intersect Hi is just the identity, and Gi plus Hi is all of C star to the m. So it's not hard to do this. Okay. And so now you reduce the problem just sort of by induction to these HIs. So now what you can do is you can let T, so consider, Vi in Hi is defined to be the elements H in Hi such that little h plus Gi is inside V. Okay? And so what is this? Well, this goes over all torsion cosets of G sub I, so all cosets of G sub I, which are contained in V. Right? All torus cosets. And so the torsion cosets are exactly the CM, the torsion points in V sub I. Right? So torsion cosets of V, sort of G sub I, are exactly in bijection with torsion points of V sub I. Okay? But now we know, by assumption, that these guys can't be contained inside any positive dimensional torsion coset. Right? Because of the word maximum here. So it's key for this argument to work if it needs finitely many families. If it wasn't finitely many families, then we have to keep track of something else. Okay, but Vi tor is, so, or let me just say either Vi doesn't contain positive dimensional torsion cosets. And so large, I won't go into in detail, but large Galois orbits plus X Lindemann implies that it's finite. Okay, and that's sort of the end. So again, the reason for doing this is somehow, what does X Lindemann do plus large Galois orbits? It allows us to upgrade from isolated torsion points in V to sort of positive dimensional torsion cosets. And then we want to apply induction on that. But if we had infinite many families to deal with, it'd be sort of hard to apply induction on that. Whereas if they all lie in finitely many families, we can reduce with this sort of parameterization argument. All right. So that's the idea, and that somehow remains the idea in general. So let me just what are the difficulties to generalizing, for example, to x1 to the n? Okay. So the basic structure of the argument still works, but it's a little trickier. At a couple points, it's substantially more difficult. So one point that caused sort of a lot of trouble is we no longer have sort of polynomial growth for free. So if you recall, what we did here was we looked at I, and we said that it influenced many integer points, and it was connected, and because of the sort of box argument, there was could only acquire integer points sort of linearly. You can't jump out of the box of IT without going through T points. Okay, so that's no longer true for SO2Z to the n. Well, non-compactness is a bit of an issue, but that's not so serious. But you really can go down to fundamental domains sort of at a logarithmic rate. So you have free logarithmic growth, but logarithmic growth is like genuinely not enough. So this point presents a substantial difficulty. Another thing that's hard, that makes your life hard, is that SO2R to the n is not abelian, but so concretely that's hard is because it contains non-normal subgroups. Right, so implicitly in all this, whenever we got a subgroup, it was abelian, and so we can find the complementary subgroup and reduce dimensions immediately. And toward the end, there's sort of a few things that go wrong with that free argument. One is that it contains sort of unipotents, tori, don't look like SL2 to a smaller power. But even something like SL2 embedded diagonally inside here is not normal. So even sort of dealing with that becomes a bit of a hassle. And is that basically it? I think that's probably... Yeah, that's probably the... I mean, another issue is this, well... No, I guess next one to the end is basically it, yeah. All right, so I guess we'll finish a bit early today, because I don't want to start with this right now. So we don't have class on Friday or on Monday, so we'll resume in 1 week. Right, thanks.